Homenade College of Engineering and Technology, Department of Electrical and Electronics Engineering, Subject Code 20EE601, Subject Name Power System Operation and Control, Unit 2, Real Power Frequency Control. So these are all the topics we are going to cover this Unit 2, Basic Speed Governing Mechanism and Modeling, Speed Load Characteristics, Regulation, Load Frequency, Control in Single Area System, Static and Dynamic Controlled and Uncontrolled Cases, Tie Line Modeling, Block Diagram Representation of Two Area System, Static and Dynamic Analysis, Tie Line with Frequency Bias Control, State Variability Model. First, the following technical terms. Control area. Most power systems normally control their generator in unisons. The individual control loop have the same regulation parameter. The individual generator turbine tend to have the same response characteristics. Then it is possible to let the control loop in the whole system, which then would be referred to as an control area. Power pole, an association of two or more interconnected electric systems having an agreement to coordinate operation and planning for improved reliability and efficiency. Electric system having an agreement to coordinate operations and planning for improved reliability and efficiencies. Prime mover, the engine, turbine, water wheel or similar machine that drives an electric generator. The purpose of a device that converts energy to electricity directly. Next one, pumped storage or hydroelectric plant. A plant that usually generates electric energy during peak load periods by using water previously pumped into an elevated storage. So the regulation, the governmental function of controlling or directing economic entities through the process of rule making and adjunctions. Next, reserve margin, the amount of unused available capability of an electric power system at peak load for a utility system as a percentage of total capability. Restructuring, the process of replacing a monopoly system of electric utilities with competing sellers, allowing individual retail customers to choose their electricity suppliers but still receive delivery over the power lines of the local utilities. Retail wheeling, the process of moving electric power from a point of generation across one or more utility owned transmission and distribution system to a retail customers. Revenue, the total amount of money received by firm from sales of its producers and or services gained from the sales or exchange of assets. Scheduled outage, real powers, load frequency control. So these basic parameters we are going to fulfill for the successful operation of the system. First one, the generation must be adequate to meet all the load demand. Second one, the system frequency must be maintained within narrow and rigid limits. So in case of interconnected operation, the tie line power flow must be maintained at the specified values. The basic speed governing modeling mechanism and modeling. Here one of the hydraulic amplifier, it is used to power plant, which is going to using for this two turbine. The steam is flow through this pumped storage system, that means the hydraulic amplifier. It will be receive the input sources. The speed changer, it will be change the speed command whether the lower and rises. The linked mechanism A is connected to the A, B and then L1, L2, C. So this kind of linked mechanism, it will be connected for the some speed governor. This governor inside it will be fixing for this one type of spring that is called a sleeve with move from upward and downward motions. Here that is called high pressure oil input is given for this hydraulic amplifier, and then another one is pilot valve. It will be controlling the oil flow directions. So this connected linked mechanism A and B and C and D and then E are it will be connected for these linked mechanisms for connected to one by ones. So model of speed governor. So first one, moment of C, that means the linked mechanism C is connected for this contribution of minus K1 Kc del Pc, that means the change in power. It will be realize the frequency change in causes of the play ball to move outwards, so that linked mechanism B move downwards by the proportional amount of K2 del F. Next one, moment of T, the contributed by the Xc and the Xe. So Xc is equal to K3 del Xc plus K4 del Xe. So next one, the moment of del Xe. So we have to changing the del X is equal to K5 interval 0 to T del X into dt. So this equation we are going to simplify this del Xc of s, del Xd of s, del Xc of s. Again we are going to taking Laplace equation of this given equation and substituting for equation 3 in 4 and then 4 in 5 and 5 in 6, we can getting this final equation for this first block. It will be included for speed governor model. So the governor model including for this comparator, it will be comparing the input signal and the reference signal for governing module. So kg divided by 1 plus stg. The output is del xc of s or del pvc of s. Next one, turbine model. So the turbine model, it will be neglecting for the incremental losses. So the turbine model del x e of s tends to kt divided by 1 plus std. The output is del pt of s is equal to del pg of s. So next one, generator model. So this generator model, it will be develop the output voltages will be absorbed by these total systems by increasing kinetic energy into the rotor, and then the frequency changes the motor load being the sensitive to speed by increasing kinetic energy in the rotor at the rate of d by dt. So we have to derive the expression for this single line load frequency control system. It will be the final equation we have to deriving for this system. So the modeling of the frequency changes for motor load being sensitive to speed. So this dividing for this equation, first the rate of change of load with respect to frequency. Second one, we have to find the damping coefficient, and then third one we have to writing the power balance equation, and finally we can find out the del pg of s minus del pd of s values. So the power system time constant del pg of s, it is compared to the total demand. The power generated to this turbine kp divided by 1 plus stb. So that is the modeling of load frequency control systems. Then second one, speed load characteristics, that means load sharing between two synchronous machine in parallel connections. So in before that, load sharing between two synchronous machine in parallel connections, we are going to first studying about the what are the necessity. We are going to connect the parallel connection of alternator, and then what are the condition we should follow this parallel connection, and what are the requirements we are going to follow this parallel connection of this circuit. So finally we can getting the load sharing of alternator. It is used to regulation of alternator. The regulation is defined as the percentage rise in voltage when full load at the specified power factor is switched off, the excitation being adjusted initially to give normal voltage. So the percentages of regulation of no load minus load voltage divided by load voltage into 100. So that is the regulation of alternator. So the percentage of speed or frequency change divided by percentage of power output change into 100. So here no load frequency minus full load frequency divided by nominal frequency into 100. So what are the necessity? We are going to connect the parallel connection of alternator. So local or regional power is used exceed the power of a single available generator. Parallel alternator allow the one or more units to be shut down for scheduled emergency maintenance time. So these are all some necessities of while connecting alternator in parallel connection. Next, what are the requirements for using parallel operation? So the output voltage rating is same, and then rated speed of the both machines are same, and then frequency of both machines are same. The kVA rating of the alternator is same. So these are all the some requirements for connecting parallel operation. Next one, what are the conditions for synchronization in alternator? The bus bar connecting for the same voltages, and the incoming machine and outgoing machine's frequency is same. The phase of the incoming machine voltage must be the same that the bus bar voltage related to the load. The phase sequence of the incoming machine is the same as that of the bus bar. Next one, load frequency control of single area systems. So del PC is the incremental control and del PD is the disturbance incremental input. The incremental control input due to change in the speed changer setting. There are two response: steady state or static response, dynamic state response. The static analysis or steady state response of uncontrolled case. So consider the speed changer has a fixed setting. So under this condition, del PC is equal to 0. The load demand changes. So here these uncontrolled cases, kg divided by 1 plus stg, that means a governing model, and then kt divided by 1 plus std, turbine model. The turbine model output is again giving to one comparator. It will be comparing for the total demand and then output of the turbine module. Though finally the comparator output is connected for this generator module, kp divided by 1 plus stb. Finally we can getting the del f of s. So this modulation we are going to reduce the block. So this block diagram reduction technique, using this figure we can reduce these block diagrams. So here del PD of s given to the comparator, and then comparator output is connected for kp divided by 1 plus stb into kg kd divided by r into 1 plus stg into 1 plus std. So the final one is the frequency is adjustable, that means change in frequencies. So del f of s equal to kp divided by 1 plus stb divided by 1 plus kp divided by 1 plus stb into kg kt divided by r into 1 plus stg into 1 plus std. So we are using for this transfer function formula here. So we have to change the load in step angle. Del PD of S is equal to del PD divided by S. So finally we can find out the del F of S, changing the using for final value theorem. So del F static condition, limit S tends to 0, S into del F of S. So we have to find out the del F saturation condition, minus Kp divided by 1 plus Kp by R into del PD. So the final one, So del F of saturation, that means the static condition is equal to minus m divided by beta, where beta is equal to b plus 1 by r. So beta is equal to area frequency response coefficient in per unit megawatts or hertz. So the finally one, del F static condition divided by del PD is equal to minus R, hertz divided by megawatts. So here R is indicating for speed regulation, del F static condition, that means steady state frequency. So del F static is equal to minus R into del PD hertz. So when several generated with the governor speed regulation R1 and R2 etc. Rn are connected to the system, the steady state deviation in frequency is given by del F of steady state condition is equal to minus del PD divided by B plus 1 by R1 plus 1 by R2 plus etc. plus 1 by Rn. So the drop of the load frequency curve is shown in the mainly determine the regulation. So x-axis considering percentage of load and then y-axis considering frequency in percentage. So effect of speed changer on speed governor system. A governor system can change the position of the main steam value which is actuated by the speed changer. Using this, we can restore the frequency to the initial value at various loads or output of the generator. So let us consider 60% of load. The nominal frequency is 50 Hz as depicted by the operating A with an incremental load of APD. The turbine speed drop and the new operating point is B and the system frequency is 49.5 Hz. It's a 99% of frequencies. Thank you.